Good morning. Today we will start MOSFET. Okay. So, we have already started, we have discussed about BJT, right, bipolar junction transistor, and today we will discuss about MOSFET. So, what is the full form of MOSFET? Metal oxide semiconductor FinFET transistor, right. So, field effect transistor. So, this MOSFET, it is right. So, we will be having a substrate or semiconductor body. Okay. So, how this MOSFET is built up, we will discuss about the structure little bit, and then we will move on to the circuit portion. So, this is the symbol of the MOSFET. Okay. By default, we have gate, drain and source. Okay. So, we have 4 terminal, but generally main 3 terminals are gate, drain and source. Okay. Apart from these, we have another 4th terminal, that is body or bulk. Okay. So, this is termed as body. Now, let us discuss about the structure of this MOSFET. So, suppose let us talk about NMOS. Okay. There are 2 type of MOS, one is NMOS, another is PMOS. So, in this NMOS, our substrate is of opposite type, that is P substrate, clear. So, if you have normal silicon, intrinsic silicon, then you dope with P type, then it is a P type substrate. Okay. On top of this P type substrate, what we will do? We will diffuse some N type element. Okay. So, this area is a, you see, N plus diffusion. Okay. And right side also we will be, so you see this area. So, on top of this P type substrate, this is a P type substrate. So, first you have a silicon area, you dope it, make it P type, then on a selected area you make it N type. Okay. So, this N is your source and this N is your drain. Generally, apart from BJT, in MOSFET, source and drain, they are symmetrical, their doping, their structure is symmetrical. So, they can interchange. Okay. So, these 2 symmetrical junction, one is our source, one is our drain, and in between this source to drain, this length we call our channel length, as if this channel which is forming between source and drain, that we will term as the channel. Okay. So, actually our majority carrier or this will flow here. Okay. So, what is, if we begin again, we have a P substrate, on top of it we are doping, suppose we want to make N type MOSFET. So, we will be doping N type source and N type drain, and in between we will grow a little oxide, you see, on top of this between source and drain we will grow the oxide. So, first step was our semiconductor substrate, and then semiconductor source and drain, and between source and drain, this region a oxide will be grown. Okay. At certain temperature oxygen will flow and this oxide region will be formed. So, these are all step by step this fabrication procedure, how to make a. So, after this oxide is grown, on top of this oxide some polysilicon, this is a crystalline structure. Okay. So, this polysilicon has like a metal, it behaves like a metal, means conductivity, it behaves like a this on top of this N type material, some metallic junction is formed to bring out the pin. Okay. So, this is a ohmic junction or metallic junction which is used to bring out the pin, clear. So, this is our substrate, and now to make a connection we need to give some voltage, right, we need to interconnect. So, this is a metallic junction and this will be formed to bring out the pin connection. Okay. So, same here in this, on top of this oxide generally this it is written metal, but this is basically a polysilicon, okay, which behaves like a metal. So, it is easy to form on this oxide, and so it is a well known structure polysilicon which is termed as this metal, and after this metal we have a oxide layer, right, and then the substrate. Okay. So, this is our symbol of NMOS. We will be discussing about the symbol of PMOS also, slowly we will come. So, by default this nomenclature we will be using. So, now you see when this MOSFET is off, okay, suppose you have not applied any gate potential and this MOSFET is off. So, this metal, this behaves as one plate of a capacitor, and in between what we have oxide, right. So, this oxide behaves as the dielectric material, clear, and it forms a oxide capacitance, clear. See, on this substrate also we have a junction for connection, that is a body junction. So, this body junction is for whole of this substrate. So, this is one of the plate and this top gate is another plate. So, this is gate, this is body, right. So, in the off state this can behave like a capacitor, and we will, this capacitance COX generally are written in terms of per area. So, we will multiply with total area. So, once again let us discuss. So, this is our gate, this is our poly, and the source or drain are of N type, we are talking about NMOS, right. So, if it is NMOS we have a P substrate, on top of this P substrate we will dope to tube this cube of this source and drain, and in between we will grow a oxide region, and on top of that oxide region we will grow a poly. So, this is our metal, oxide and semiconductor. Now, in between this source and drain, this length what we term as channel length, L is our length. Okay. Now, this channel length, you see the physical length should be supposed to from this point to this point, right, but maybe this region it may grow little bit because this is in all in micrometer length, right. So, it is very difficult to control. So, this may little bit, it may diffuse little bit. So, the actual L that we were trying to draw and the what is physically the distance, that may differ little bit, that is because of the implementation uncertainty, because at this micrometer length it is difficult. Okay. So, this is known as the L drawn, that was our actual target, and this is our L effective, and this difference is lateral overlap. Okay. So, we may have a, so this is L effective is little bit less, okay, that you understand at this moment, that whatever this area, this is our W and this is our L, okay, but this L it may be little bit less. Okay. Let us consider this at this moment. Now, when we grow a PMOS, previously we had a NMOS only technology or PMOS only technology. Okay. So, in NMOS we only grow P substrate, on top of this P substrate we grow this N plus region. but nowadays the technology is advanced. So, on the same platform we can make both N and P, and that is termed as CMOS. Okay. Previous technology it was only NMOS. So, you can make only NMOS devices. Then after some time PMOS only technology also where it was developed, and nowadays we can have both N and P, it can be fabricated on the same wafer, same substrate. So, this is termed as the complementary metal oxide semi. Complementary means N and P are complementary. So, we use both of them. So, it is CMOS. So, NMOS we already know that it is a on top of P we are building some N region source, N region drain, in between them on top of them we grow a oxide, and on top of this oxide we grow a poly, right, poly oxide. And what is the substrate connection? This is P type. So, you see it is written P plus. P plus means doping is little bit higher. Okay. This is known as N plus. Okay. Doping is little bit higher. So, this is our body or substrate. Now, to make it a PMOS, what we will do? PMOS, what we need? We need just to invert it. So, we will need a N type substrate. So, this is by default it is P. So, what we will do? We will make a well, big well or tub, and we will dope it with N type. So, now this tub will behave like the substrate for this MOS. Previously this was our substrate. Now, on this substrate we build a well of N. So, this N now will behave like this substrate. On this N we will dope P, P type source, P type drain, clear. And what is our bulk here now? This is N. Previously for NMOS it was bulk was P. So, for PMOS bulk will be inverted N. Okay. Rest of the procedure is same. So, that is what is our structure. Now, let us apply a voltage, that is VGS. So, what is the first step? First step is substrate is grounded. See, this substrate and this source or substrate and this drain, we do not want any current. We want our current to flow through channel, right. In BJT if you recall, collector and emitter current were flowing, right. So, similarly we want drain current and source current. Okay. And in this MOSFET, as there is a oxide region, so gate current is 0, right. You see, between gate and the channel, in between what we have? We have oxide layer, na. So, no gate current can flow. So, if our gate current is 0, then whatever is our drain current, that should be our source current. So, in MOSFET Ig is equal to 0 and Id is equal to Is. So, it is simplified than BJT. In BJT we had 3 current, small base current and collector and emitter current, and collector and emitter current nearly equal, right, and we have this exactly equal. Okay. So, drain current and source current are same, and they are also symmetric also, okay, physically also symmetric. So, what is the difference? Difference is that no current flows through gate. Now, suppose this P substrate and this N substrate, I do not want any current through them, right. So, this is a P type and this is a N type. So, if they are forward bias, large current will flow through this diode. This will form a diode type structure, na, P and N. So, I do not want any current to flow through the fourth terminal. This fourth terminal I do not want any current. Okay. I want current through the drain to source in the channel. I want current to flow in this region, not through this substrate. This is will be not of use. Okay. This is a, so this diode should be in reverse bias, right. So, P should be connected to what? Lowest potential available, so that it is off. So, what is our lowest potential? Say ground. So, it will be always for NMOS, our substrate is P na. So, P should be always grounded. Why? Because we do not want any current to flow through substrate, we want current to flow through channel is of our interest. Okay. So, this should be always you see grounded. Okay. Now, let us start with source is also grounded and little bit potential is given at drain, and gate we are starting from 0. Okay. From 0 we are building up this voltage, gate voltage. Okay. So, now let us consider that this is a P substrate, and if you give a positive voltage here, it will repel the holes, right. If holes are repelled, what remains? Immovable ion, right. For P type substrate, if you remove the hole, then negative ions remain, and these ions are heavy, right, they cannot move, that is why we term this immovable ion. So, if I apply a positive potential at gate and start from 0, slowly I am building up this voltage. So, what will happen? This positive voltage on the gate electrode, it will repel all the positive holes below it, right, below the channel. So, this positive potential will repel all the holes. So, all the holes will move down. So, if holes are removed, then this they are not balanced, right, this minus and holes plus, holes means absence of electron, right. So, it was balanced, neutral, electrically neutral. Now, the holes as it is removed, it becomes a ion, minus ion, negative ion, right. So, what will happen? Suppose the charges, number of charges on this positive plate will be equaled by this number of negative ions. So, they will just form like a capacitor, two plate of capacitor, right. Okay. So, one is oxide layer and another is depletion layer, right. So, this parallel plate is formed, one plate is our gate, another plate is our body, and in between we have dielectric layer, one is oxide layer, another is depletion layer. This is our depletion region, right. In reverse bias what happens? A depletion region is formed, na, space charge region. So, this is that space charge region. Okay. So, you see this is a capacitance, one is the oxide capacitance and another is the depletion capacitance. So, the MOS will behave like a capacitance at this moment, still it is not on, right. Now, what is happening? We are still increasing this voltage. Okay. Now, if this becomes more positive, then at after a certain threshold voltage, what it will do? This positive voltage will attract electron, right, electrons will be attracted by the positive voltage. So, what will happen? This N plus and N plus source and drain region, they have large number of electron. So, this electron will be attracted towards this positive potential. So, they will come up, okay. They will come and make a as if a layer. So, previously it was of P type. What is the majority carrier in P type? Holes. Now, if I apply a positive voltage at the gate, and if this gate voltage is above a certain potential, threshold potential, what will happen? This positive voltage will attract electron and this electron will come up in the channel. So, this channel was originally having the majority carrier as holes, now it is having electron. So, what we will say? The channel is inverted, inversion of the channel layer, right. Previously majority carrier was holes, now because of this positive gate potential what happened? First a depletion layer will be formed, even if you keep on increasing, then a pool of electron will form. So, this we will say that it is a channel, right. and this channel we will see that when this channel is formed we will call this that channel is inverted. And next if we apply a positive drain potential, what will happen? This positive drain potential will attract all this electron in this direction, and from source to drain what will happen? Electron will flow. So, current we will say that in opposite direction. So, current we will say that from drain to source a current is flowing, right. Electron is flowing like this. So, we will say that current is flowing like this from drain to source, okay, because current direction is opposite of the electron movement. So, as if see electron is coming from this direction to, if I apply a positive potential it will be attracted towards this, but the current direction as if it is coming from drain and collected at source, that is why this terminology. Okay. But in others way this source is sourcing the flow of electron and drain is making it to flow because of this positive potential. Okay. So, this is how the MOSFET works. Okay. So, this threshold voltage that we termed, this is the minimum voltage after which the channel is inverted. Okay. This depends on the work function difference of this gate and this source and drain region, and this Fermi voltage twice phi f, and the oxide will also, in oxide Q is equal to C V, right, or V is equal to Q by C. Because of those oxide it will also offer some voltage. So, this total voltage depends on this V is equal to Q by C plus flat band voltage and work function difference. Okay. So, after this threshold voltage the MOSFET will term that this is turned on, and after this threshold voltage the channel is inverted. So, this is when suppose you are starting with VGS only and source and drain both are 0. So, first step is what? A depletion region will be formed, right. So, this positive potential it will repel all the holes towards down, right. If holes are repelled, what is remain? Negative ions. So, this region is formed is depletion region. Okay. Next, suppose you are increasing this voltage further. So, what will happen? This positive potential will attract electron and will make a inverted layer. Then if you apply a positive drain potential, then current will flow. Clear? So, first step is that, first step is forming of depletion layer. Your Vg just started from 0, then your Vg is just greater than Vth. What will happen? Channel inversion or a layer of electron. Okay. Then suppose your Vg is higher than Vth as well as Vd is also higher than 0, then what will happen? Current will flow. Next step is we have a higher Vgs greater than Vth and we also apply a small Vds. So, this higher gate voltage will attract electron and a channel will be formed, right. So, we have a source region, we have a drain region. Previously there was no channel. Now, what happens? A channel of electron is formed, and now if we have a positive drain potential, so electron will start to flow or we can say current is flowing. This is the operation of the MOSFET. So, this MOSFET will only work above VTH. So, the VGS, the voltage it is above threshold voltage is known as the overdrive voltage. Okay. This terminology is known as the overdrive voltage, VGS minus VT. So, we will discuss about the current equation. Let us this mu n and COX, you see COX is our oxide capacitance, okay, and mu n is our mobility of the electron. So, these two term is turned this Kn, this is known as the process transconductance. This is a process parameter, this mu n COX is known as the process transconductance parameter. Now, if I plot ID and VDS, what is happening? First step is to you have to VGS greater than VTH, then it will turn on, right, then only it will be on. Before that it is, suppose your VGS is less than VTH. So, it is in which mode? Cutoff mode. First condition is that gate voltage has to be higher than the threshold voltage, otherwise it will be not on. So, this is VGS greater than VTH, that is it is turned on. Once this is turned on, then suppose we are increasing the VDS voltage. So, initially it will follow a linear relationship, okay. Initially it will follow a linear relationship, then what will happen we will discuss. So, suppose you are increasing this VDS, what is this channel potential? Channel potential is VGS, right, and VGS when it is above VTH, channel is formed, that we know. Now, when drain is also 0 and source is also 0, this VGS is uniform throughout source to drain, right. When this source is also 0 and drain is also 0, then VGS is uniform, get to source voltage at the source end and at the drain end, they are this channel, the field of this channel is uniform. Now, if I suppose increase the drain potential, then this drain potential will fight with this gate potential, right. So, this is also positive and this is also positive. So, this drain side our field is reducing, is not it? Source side our potential is 0, but drain side our potential is higher. So, it is something like this, na? Source side our potential is 0, but drain side our potential is Vd and gate side our potential is Vg. So, this difference is VGS maximum at the source end, but this difference is VGS minus VDS at the drain terminal, and that is less. So, that is what will form a tapered channel. Suppose your gate voltage is higher than threshold voltage. So, a channel will be formed. Now, we have increased your drain potential. So, what will happen? This drain potential will reduce this vertical field. Previously at the source end it was only VGS. When drain potential was 0, it was also VGS. Now, you are applying a potential of VDS. So, this potential is reduced to VGS minus VDS, okay. And when VDS will be just equal to, suppose when your channel is formed at this VGS minus VTH, after this your channel just starts to form, right. So, beyond VTH your channel starts to form, or otherwise when VOV is 0, VOV is 0, 0 means VGS is equal to VTH, after this your channel starts to form. So, when my VDS is equal to VOV, what will happen? This channel will just end here, this channel it will just end here if this VDS is equal to VOV. At VGS is equal to VTH, my channel just starts to form, and VGS greater than VTH, channel is increased, right. So, we can say when VOB is equal to 0 or VOB is equal to VDS, this channel just ends at the drain terminal, and if you increase VDS greater than VOB, what happens? This channel will move away, because there is now no potential to form the inverted channel. So, if you increase this, so this channel will end early. So, this is known as the tapering of the channel. How this tapering is happening? With the drain potential. So, this is our ID versus VDS plot. So, this region we will know in MOSFET, it is known as the triode region or linear region. This terminology of this region is different than the BJT. In BJT we call this region saturation region. Na? In this it is termed, terminology is just different, do not get confused, and as it is well known. So, this terminology remains undisturbed. So, when this is, you see, initially this ID and VDS, they are nearly linear. So, this region is our linear region, because ID VDS is nearly linear, just like the Ohm's law. And once this threshold voltage is, once this overdrive voltage is crossed, so what is happening? This channel is tapered, and after this channel is moved away from the drain junction. But because this is having a high potential, this VDS is high, na? Because this is having a very high potential, so this electron, although there is no channel and this distance is very short, this is a short channel device. So, this electron they jumps from over here, and it provides you a constant current. So, as this VDS is high, so after this potential VDS is equal to VOB or greater than VOB, after this point, this, because of this high field, this electron just jumps over and the current is a constant, almost constant. We will come to this, that like the early effect there will also a little bit increase, and we will discuss this. So, we can say that in this current is saturated, current is not increasing means current is saturated. So, this is known as the saturation region. Okay. So, in this region what is happening? Current is almost linear to the voltage. So, it is linear region, and beyond this VDS sat, you see VDS saturation is VOB. What is VOB? Overdrive voltage, VGS minus threshold voltage. So, this is our VOB. So, this is the junction where the MOS enters into saturation region. So, in saturation region it is behaving like a constant current source, right. You see current is constant. Okay. So, this is the current and VDS plot. We will discuss about this current equation and different regions again. So, that is what is happening. We have a channel formed, and if VDS is equal to 0, this channel was uniform, first channel was uniform, provided that this is 0, this is also 0, and we have a positive gate voltage. So, we have a uniform channel. So, this is our 1. In 2, we are providing a positive drain potential, and that is say just equal to VOB. So, this channel will just end at the edge of the drain. Now, we are even increasing this drain potential, the channel will move away. So, this is known as the pinch off, this is just ending. So, at this end, what is our vertical field? VGS minus VTH minus of VDS, and VDS is also VGS minus VTH. So, this field is just 0 at this end, and at this end as there is this VDS is higher. So, this is opposing this vertical field and the channel moves away to the left. So, this is our channel pinch off behavior. Now, can you tell me, previously my channel length was L, and as I increase my VDS, channel is moving away from the drain. So, this channel length, suppose this is L1 and this is L2, which one is higher? L1 is higher, no? So, if we increase the VDS, what is happening? As if my length is decreasing and my current is proportional to W by L. So, if L is reduced, what will happen to the current, increase or decrease? If L is reduced, what will happen to the I? It will increase. So, that is why this, as my VDS is increased, as my VDS is increased, my as if channel length is decreasing, and so my current will increase. That is why it is not flat, it actually slowly increase. Early effect, you remember early effect? If you extend this, they will cut off and meet at same, but in MOSFET this is happening because of the channel length is changing, na, channel length modulation. So, I will discuss this again. So, it will initially it will take a little bit time to get acquainted with MOSFET, okay. And I will give you assignment, those who have not joined the MS team, please join the MS team.